Hi everyone, in this video we are talking about section 4.1 in your textbook, and chapter 4 in your textbook is really my favorite chapter. So we're talking about linear regression and correlation between two variables, and how to build the very simplest kind of predictive model using real-world data so that we can build a mathematical model which is just a function that takes an input and provides you an output, where your input is something that's maybe easily measured, and your output's going to be a prediction that's going to be useful in some way. So I think chapter 4 is full of really good stuff, so much to the point where your project this semester is going to be over the content of chapter 4, and so it would be important to really pay attention during chapter 4 and make sure you understand what's going on, because again, the project is a big deal. We're going to be working on it for several weeks, and it's going to be a significant part of your term grade as well. But here we go, 4.1. We're talking about two variable statistics now. And so whenever we have two variables, we're going to label them so that one of them is going to be called our response variable and the other is going to be called our predictor variable. And I want you to know that these two words, predictor variable and explanatory variable, these are synonymous. And what that means is you can use those two interchangeably, and you might see them appear either way on like an exam, right? And so what this is saying is number one, our response variable, that's going to end up being the value that we want to predict whenever we're talking about the world of creating a linear regression model. We want to be able to predict our response variable. Now, the word predictor variable is a predictor variable because we use measurements of our predictor variable to make a prediction about the response variable. Right, so we want to use the predictor to make a prediction about the response variable. And so hopefully that helps you remember the role of these two variables and how we're going to label them. But also, like I said, predictor and explanatory are synonymous because we could also say that we want the explanatory variable, or maybe I should say we want changes in the explanatory variable to explain changes in the response variable. And so both of those are valid ways of describing what goes on when we build a linear regression model that illustrates, the relationship between two variables. And of course, one of our variables is going to be this response variable, and the other variable, you could call it the predictor variable, you could call it the explanatory variable. And those mean the same thing because you could describe the relationship in two different ways, right? Here we go. As an example, suppose that you work for Nintendo. So Nintendo released a game console called the Wii, and on the Wii they had a game called Wii Sports. And in Wii Sports, you had a little remote controller, and you would swing that through the air whenever it was your turn to be at bat. And if you swung it at the right time, you would hit the ball. And if you swing the remote faster, that would be analogous to swinging a baseball bat faster. And so then the ball should go farther in game whenever you hit it. So if you swing the remote control very quickly, then there's a good chance you might hit a home run, for example. You might hit the ball out of the park. And so let's say that you want to make this very realistic. And to make sure that our game is really realistic, we're going to build a model that can predict flight distance from bat speed. right? So we want to be able to predict the flight distance. And so that means that this is our response variable. And you could also call that the explanatory variable. Nope, no, sorry. My bad. Not true. Flight distance is the response variable, and we want to use bat speed to predict this. So bat speed is the predictor variable, and again, predictor and explanatory are the same. And the reason this is because we want to say, I can use the bat speed to predict the flight distance of the ball, or you might say that the bat speed explains, how far the ball is traveling. So what you would want to do is actually gather data from real life. If you want your game to be realistic, then let's go out in the real world to a baseball game. We're going to record both the bat speed and the flight distance of every hit that we observe whenever we're watching the baseball game. And by the way, what you would then do with that is you would build this math model, which is a math model is just a function. And the function is then going to tell you a good approximation of a flight distance whenever you're given a bat speed. And then you might use this in your video game so that whenever you measure the speed of the controller moving through the air, whenever someone swings the remote control, the video game would be able to give you a flight distance. You'd be able to see the baseball on the Wii Sports game flying through the air at a certain distance in response to the speed at which you're swinging. Okay, now a new example. Suppose that you work for Midland College and you want to determine whether attendance correlates with performance. Right? And so you're going to record the attendance of each student and you record the exam scores of each student. And so here, my response variable that I'm measuring is going to be the exam scores of each student. And what I want to be able to use to predict a student's exam score is attendance. So attendance is our predictor variable, or you might call our explanatory variable. Again, we call attendance a predictor variable because maybe before an exam, I can look and see how many classes a student has attended, and I might be able to use the attendance record to predict the exam score of that student. Or maybe you in a different sense, in a different perspective, maybe we already have the exam scores and I'm looking at the differences in exam scores between students, and I also take a look at the attendance record of each student, and I might be able to say, that the attendance record of the students explains the differences in the exam scores. So let's talk about types of correlation. So here, in this first chart, this is a linear positive correlation between this value, this variable, which we might call x, since it's represented by the horizontal axis, and this variable, which we might call y, since it's represented by the vertical axis. This would be a linear positive correlation, and it's linear because all of the dots appear to fall along this line or near to it, hence that's why it's linear. And it's positive because it's increasing from left to right. So if that line seems to be increasing as we can move across from left to right, that's what we call a positive correlation. So this is linear positive. Then this next one, you might be able to guess, all of the points seem to fall around a certain line, or at least near to that line. But this time the line is decreasing from left to right. And so maybe this shouldn't be a surprise to you, but this is going to be called a linear negative correlation in the second graph. Negative because it's decreasing in value as we go from left to right. Okay, the next correlation is what I would call nonlinear, because these data clearly follow a pattern, but it's not a line. So this is what happens when there's a clear pattern to your data, but that pattern is not just a line like it was for our first two graphs. And then lastly, We say that we have no correlation if the dots just seem to be scattered about the sample space with no particular pattern, right? So if we don't actually recognize that the dots are arranged in any kind of pattern, this is just no correlation. And maybe you say, well, the dots seem to be occupying kind of a circle. That could be a pattern. But notice that that pattern of circle doesn't allow me to make any sort of prediction about this y variable if you told me the value of the x variable, right? So if you told me the value of the x variable was 12, and you say, well, can you tell me specifically what you think the y value will be? Well, I have no idea, right? This doesn't help me at all. The pattern isn't a type of pattern that I could use to build a functional model to make predictions. All right. Now, types of correlation, linear positive. We also call this positively associated. And so I want you to know that these things, a linear positive correlation, and if you hear someone describe two variables as being positively associated, these are again synonymous. And so we can use those terms interchangeably. And then likewise, if you say that the correlation is linear negative, you could also say for the same two variables that those variables are negatively associated. And those are also equivalent ways of describing this. Okay. We also talk about strength of correlation. And so with regard to the strength of correlation, the strongest types of correlations are perfect correlations. And so this is perfect because all of these dots lie directly on top of a specific line. So I can draw a line and every single measurement lies exactly on that line. There's not even a little deviation. We say it's a strong correlation if these dots fall pretty close to a given line, and that's not the best line, but if I draw a best fit line to this data, all of the dots are pretty darn close to it. This, in yellow, is what I would call a moderate correlation because I could draw a line and see that the dots are pretty close, but some of the dots are straying actually somewhat far away from the line. So it's not quite as strong as this second graph. And then in this last graph, we call it weak because, again, I can still make a linear best fit line, but I actually have some significant outliers here. So the farther your dots are straying away from the line, that means we have a weaker correlation going on. Okay, so then this is what we call the linear correlation coefficient. And so make sure that you know what this means whenever I say linear correlation coefficient. The symbol for a linear correlation coefficient is just a lowercase r. So whenever I represent this in a formula, I'll say lowercase r is equal to all this junk. And again, this lowercase r, the linear correlation coefficient, is going to be equal to the sum. Remember, capital Greek letter sigma means we're taking a sum. So we're taking a sum of this and this z subscript x times z subscript y. Those refer to the z-score, which we talked about in a previous video. These refer to the approximate z-score for a particular x value and a particular y value for a given experimental unit, you would say. So any experimental unit in your experiment, you're going to take that unit and you're going to measure both the x value and the y value. So you're going to make two measurements because we're talking about two variable statistics. So you're going to measure two variables for every experimental unit. And then so what you're going to do is multiply the two z-scores that you get for those measurements. And again, reference an earlier video if you forgot what the z-score is. And then we'll do a little example, I think, later on in this video too. N is the number of data points, and so we divide by n minus 1, just like we divided by n minus 1 whenever we were calculating the sample variance. Now, values of the linear correlation coefficient. The values of the linear correlation coefficient are always greater than -1, or you could say equal to -1, and less than or equal to +1. This is always the case. And so if you are calculating your linear correlation coefficient on an exam, and you found that your linear correlation coefficient was something like 3.1, well, then you've done your math wrong. You need to start over and try again because it has to be less than +1. And if you found your linear correlation coefficient was like -2, well, then again, you did your math wrong. So it always has to fall inside this interval where it's greater than or equal to -1 and less than or equal to +1. If we have a linear correlation coefficient of +1, that means you necessarily have a perfect correlation, a perfect linear positive correlation, where all of the dots fall exactly on top of a line. And so R equals +1 means a perfect linear positive correlation. If you have an R of like 0.97 or something that's close to +1, this is a strong linear positive correlation. If you have an R value that's like around 0.74, this is what we would call a moderate linear positive correlation. And if you have a weak correlation, you might calculate an R value of something like 0.46. And so what I'm trying to say is that the values of R are actually describing the strength of the correlation. So if you're closer to 1, then you're talking about a stronger correlation. And if you're closer to 0, you're talking about a weaker correlation. So this is why you might want to calculate the value of lowercase r, because it's actually putting a number to the strength of the correlation. We're quantifying the strength of the correlation. And so that's pretty nice. Likewise, if you have a negative value for r, then we're talking about quantifying the strength of a negative correlation. So then a negative r value implies a negative correlation. So if I have -1 as my r value, we're talking about a perfect linear negative correlation. If I have something that's just very close to -1 but not quite, then we're talking about a strong linear negative correlation. If we're talking about something like -0.77, I would call this a moderate linear negative correlation. And then again, if it's around -0.5, I would call that a pretty weak linear negative correlation. So just to summarize what I've already talked about. If r is positive, we say that our two variables are positively associated or positively correlated. If r is positive, then that means our response variable is going to increase as the predictor variable increases. If r is negative, we might say the variables are negatively associated or negatively correlated. And if r is negative, that means our response variable is going to decrease as the predictor variable increases. So by the way, whenever we represent data in a scatter plot on a plane, the horizontal axis is always the predictor variable, or remember, we can call that the explanatory variable. And the vertical axis is always representing the response variable. Now, if I, like I said, r is always less than or equal to +1, and it's always greater than or equal to -1, and this is always true, then that means the absolute value of r, where those vertical lines mean absolute value, the absolute value of r is always between 0 and 1, right? Because absolute value just makes it positive. So if the absolute value of r is small or near 0, we say that has no correlation. If the absolute value of r is mediocre, we say it's a weak correlation. And if the absolute value of r is large, we say it's a strong correlation. this is just another way to summarize what I've already said before. If you calculate r correctly, then r always falls somewhere between -1 and 1. Again, I'm repeating myself, but it's because these things are important. So here I have a number line, and if we've calculated r correctly, then that number is going to follow somewhere here on this number line as I've portrayed it. And here are kind of the zones of the number line and how you might describe them, right? So if r is close to -1, we say it's strong negative correlation. If it's close to +1, that's a strong positive correlation. And if it's close to 0, there's no correlation. And in between, in these little yellow zones, we say it has a weak or a moderate positive or negative correlation. And so maybe you can't see this, it's not super obvious, but I'm actually going to put little visuals on this slide that represent, you know, what it might look like to fall anywhere along this little number line, where this number line represents values of r. So if you have a -1 value for r, that's a perfect negative correlation. And if you have, you know, something in the green zone, that's just a strong negative correlation, so it looks like that. In the yellow zone, we have, you know, a moderate negative correlation, a weak negative correlation, no correlation, again, just looks like dots scattered around, so that right there, that graph, that scatter plot has an r value of 0. And then moving to the right, you can see the data points are sort of starting to regroup into a line, and then, of course, +1 is a perfect linear positive correlation. So take a moment to look at those scatter plots and try to get a feel for what it looks like scatter plot wise for different values of r on the spectrum between -1 and 1. Okay, so if we were to ask the question, does a linear correlation exist between my two variables that I've measured or not? Right? We want a yes or no answer to this question, right? And we want to find a way to do this with numbers, right? Because we're in a math class, we're trying to get definite answers here, not just qualitative answers, not just I'm going to eye it and squint and see how I feel about it. We're actually trying to put numbers to it and then answer this question definitively. And so what we're going to do is we're going to identify regions of this number line where we say, yes, there is evidence for positive association, or yes, there is evidence for negative association, and also places on this number line where we say, no, there's no evidence for a linear association between these variables. And we're going to divide up these regions on the number line by what we call critical values. And so somewhere between 0 and 1, you're going to find a critical value, and then somewhere between 0 and -1, you just take the negative of whatever our critical value was, and that's where we're going to place this barrier. And I just want to point out these barriers, the critical value and the negative critical value, these are dividing up your possibilities, the possible values that you might calculate for r, into regions where we say, yes, there is evidence for an association, or no, there is no evidence, or not enough evidence is probably a better way to put it. Oh, and before I move on, what are these critical values? How do you know what they are? Well, let me show you our Canvas course homepage. So here we are at Statistics Web with Maca, and I'm on the course homepage in this little tab. If I go to this link that says Nice Comprehensive Formula Chart, I think that it's here, and if it's not, I will make sure to find it for you regardless. We're going to try this location first. So again, if I haven't said this before, this formula chart is what you're going to be allowed to use on your exams, including the final exam. So try to become familiar with this formula chart and see what formulas it offers so far this semester for Chapter 2, Chapter 3, Chapter 4. And if you see a formula here, that means you don't have to memorize it for the exam. because you're going to be allowed to use this chart for any midterm or final exam. I like this chart because it has things organized by chapter, and what I want to point out is at the end of this formula chart we have a bunch of tables, and here we go, just what I wanted to find. Table 2, the Roman numeral 2 here, is telling you critical values for the correlation coefficient. And this might be small, but again, the point is I want to show you where to find it. You can find it on your own and take a closer look if this doesn't show up well in the video. But I also want to point out something about this table of critical values. It's that it gives you a new critical value for every value of n. So n, lowercase n, is your sample size. And so that's the number of experimental units that are appearing in your experiment or in your survey. And I just want to point out to you then that if you have a smaller number of experimental units, or maybe that means you surveyed fewer people for your study, then the critical value is really, really high, like it's almost 1, because you can't conclude a correlation between two variables with very much confidence if you have only 3 people surveyed, or 3 experimental units, right? 3 is not a large enough sample size to be doing statistics with. But you'll notice the critical value, remember the critical value is just the threshold for what we use to consider, consider it a correlation. If we're above the critical value or below the negative critical value, what we're saying is, yes, we have enough evidence to claim a correlation here. And notice that that critical value threshold decreases when your sample size increases. So it's important whenever you're conducting an experiment or a survey to get as many people sampled, or get as many experimental units as you can, get the largest sample size that you can afford to get, because a larger sample size is going to make it more likely that you can make a claim, right? More likely that you can claim a correlation between variables. And these numbers, these threshold values, they're not chosen arbitrarily. There's also a very rigorous, probability-based math proof that you can look up and find how they calculate these critical values and why it makes sense. But that's really outside of the scope of this course. I'm really not trying to introduce anything in the statistics course that would be, outside of the scope of what a freshman math student would be able to handle, because I don't want to add undue burden to your lives. And so what we're going to do is we're just going to look at this table 2. We're going to use our sample size to look up the critical value for the correlation coefficient, and that's what we're going to use to determine whether or not we have a correlation. Okay, now you know where to find it. You know where to see it on your formula sheet during an exam. We can move on. Now, you've probably heard this before. It's a little bit cliche, but correlation does not necessarily mean causation. What you do whenever you try to conduct an experiment is you try to, have a control group, and you try to remove any confounding lurking variables, and so that you can have more certainty about this. But just because your predictor variable, or you might say just because your explanatory variable, is correlated with your response variable, that doesn't necessarily mean that the predictor variable causes the response variable, right? So a change in the predictor variable doesn't necessarily cause a change in the response variable just because you find a correlation. So one thing that we've mentioned before, and I will mention again now, is that you might have a lurking variable, and that might be the reason why you see a correlation, but the causal relationship doesn't exist between your predictor and your response variable. And so what a lurking variable is as a lurking variable is a certain variable where changes in the lurking variable actually cause a change in the predictor and a change in the response variable. And that's why we observe a correlation when actually there's not a causal relationship. Really the causal relationship whenever you have a lurking variable is saying that the lurking variable causes the changes in each of the two variables that you measured, right? It changes the predictor and changes the response. So in my example, I'm sorry if I'm reusing this from previous videos, but studies have found that people who drink coffee live longer. And so sometimes I read articles on the internet that try to make this claim. They try to say that drinking coffee causes people to live longer. And they make this claim about causation because what they've observed through many, many studies is that these two are correlated, that drinking coffee is correlated with living longer. However, like I've probably pointed out before, I've also read articles on the internet that say no, there's actually a lurking variable here. And the lurking variable might be something like, I don't know, like certain cultures enjoy drinking coffee and drink coffee on a regular basis, and other cultures don't. There may be some other cultural factors then that are affecting the lifespan of a human. And heck, maybe a lurking variable might be like wealth, right? Because if you're really wealthy, you can afford to buy the best coffee maker and the best coffee, or maybe you can afford a $5 cup of Starbucks coffee every morning. And wealthier people might be more likely to be drinking coffee. And at least in the United States, if you're wealthier, you have better access to things like healthcare and nutrition and facilities where you can work out and that sort of thing. And so if your lurking variable is something like wealth, that might cause you to be drinking more coffee, and your lurking variable, which is something like wealth, might also cause you to live longer. And so if the lurking variable that's causing the changes in both your predictor and response variable, then that means there's not necessarily a causal relationship between drinking coffee and living longer. We just observed a correlation because some lurking variable that we didn't measure for is actually producing the changes in both. Hopefully this makes sense. This, by the way, lurking variable, this is one way that you might have a correlation without causation, right? This is one of the ways. I'm about to show you another way. And this is called a spurious correlation, so make sure we're familiar with this vocab word and the definition. And a spurious correlation is a correlation that just happens out of random chance. And it's good to illustrate this with an example. And what I've put on the screen here is a scatter plot. Well, actually, it's more like time series data. This isn't what I would call a scatter plot. This is what I would call a trend, because we're representing time series data. But in blue, these blue dots represent measurements of pounds margarine consumed per person in the state of Maine. So what they're saying is they have the population of Maine, and they know how many pounds of margarine are consumed in Maine, because they can look and see, for each grocery store, how many pounds of margarine did they sell, and for each restaurant, how many pounds of margarine did they use. And so we have this value of pounds margarine consumed per person in Maine. And for every year, like 2000, 2001, 2002, and so on, we have this value recorded, and that's what represents these blue dots. So this would be like 8 point something pounds of margarine were consumed per person in the year 2000 in the state of Maine. In orange, we're representing the divorce rate per 1,000 individuals. So again, if you divide the number of divorces divided by the population in Maine and multiply by like 1,000, we get these orange dots. So these orange dots are telling you basically the number of divorces in the state for each year between 2000 and 2010. Now, it may not look like these are extremely well correlated, but really if I had rescaled my y-axis for the orange dots, you'd be able to be a little bit more sensitive to the changes in the orange dots, because whenever these blue dots go down, for the most part, the orange dots are also seeing a little bit of a decrease, but it's just not as pronounced the way I have my y-axis scaled. But this is actually a really, really strong correlation. And to illustrate it even better, what I'm going to do is actually use a scatter plot for the same data, so the same 10 measurements for both of these two variables. I'm going to put these 10 measurements on a scatter plot. So now my x-axis, or my horizontal axis, is representing my predictor variable, which is the pounds of margarine consumed, and my vertical axis is now representing the values of my response variable, which is the divorce rate. And this, I hope you'll agree, shows a very strong positive linear, that's the word, positive linear correlation. So these two variables have a very strong positive association. So you might be tempted to say that since these variables are correlated, that must mean that consuming margarine leads to divorce, that there's some sort of causal relationship between eating margarine and getting divorced. But then again, if maybe you recognize how silly that is, so you don't maybe you don't fully subscribe to that theory. And so we would say that actually this is a spurious correlation because it happened out of random chance. But I mean, even whenever I calculate my linear correlation coefficient, remember lowercase r stands for linear correlation coefficient. It's 0.993, so it's just so close to positive 1. This correlation is so close to being a perfect correlation, it's almost spooky. But clearly, this happened out of random chance. Clearly, there's not a causal relationship between these two. Now, here's another example. And let's, I think we're going to have to actually work through this. But that's good. Nice to see an example worked. It says, suppose you work for the City of Midland Parks Department. One measure of your job success is going to be the number of times that citizens use a set of city hashtags on social media. And so, like, you're like the social media public, public engagement person, and your boss is trying to measure how good you're doing at your job. And so one of the ways your boss is going to measure how effective you are is by watching the social media sites, Facebook, Twitter, Instagram, whatever, and looking for the city's hashtags and seeing if the citizens or residents of Midland are actually using city hashtags. And the thought here is that if they're actually using the city hashtags, then that means that the public is engaged with the city and that you're doing a good job. And so maybe you have a theory. And your theory is that whenever people come to the annual 4th of July fireworks show and they see a big fancy display, those people are going to be more likely to post about it using hashtag Midland is poppin' on their social media website. So what we're saying is that a really large fireworks show is going to have a causal relationship with hashtags used. So more fireworks means more hashtags used. That's your theory. And so what you do is you collect data over the course of like 3 or 4 years, 4 years here. Collect data over 4 years, and we're going to look at the money spent on fireworks in terms of thousands of dollars at the City of Midland fireworks show. And so it looks like, in 2010 we spent $90,000, and in 2011 we spent $70,000, and in 2012 we spent $110,000 and then $130,000. And then you also look at the number of posts using the city's hashtag Midland is pop and hashtag, right? And so this is how it correlates each year. And so we're going to draw two scatter plots of this data. Number one, we'll represent this as time series data. And then number two, we're going to create a different scatter plot to view the correlation. And so, by the way, whenever we represent time series data, we also call that type of data visual a trend. Now let me just check, but I'm pretty sure I don't have this created already. Yeah, I don't. So let's get out Microsoft Excel, and we're going to put in this data here, and we're going to see if we can create those two trends ourselves. So 2010, 2011, 2012, and 2013 are now in Excel. It's pretty good. And this is going to be money spent on fireworks in this column, and then number of hashtags in this column. So fireworks, the money we spent on fireworks was per year 90,000, 70,000, 110,000, 130,000. The number of hashtags we viewed was 330, 440, 350, and 490. So I've recreated this table in Microsoft Excel. And what I first want to do is represent this as time series data. And so what I'm going to do is just select this whole range of cells, go up on the ribbon to Insert, and then this here says Insert Scatter. I'm going to do that, and I like this one with the straight lines whenever I make trends. And so I'm going to delete the chart title because I think that looks ugly. I'm going to go over to Home, and I'm going to make these grayed out values actually black, because default charts in Excel make black characters or black font. And, no, let me go back. Default charts in Excel make the font color gray, but that doesn't look good. It looks much better if the font color is black, because it's actually going to stand out more on a PowerPoint or a paper, and it's going to be easier to read. So that's why I try to make the font color black. Same thing for this legend. Make that font color black. I don't like my x-axis because these are years, and so it looks silly to me when I see 2009.5. I can actually fix this though. So if I click on the x-axis, maybe right-click on the x-axis, and I click Format Axis, over here where it says minimum, I'm going to set the minimum value to 2009, and where it says maximum, I'm going to set the maximum value to 2014. And then I'm going to make sure the major unit is 1, and so that will actually make sure my years down here don't show like 2011.5 or something silly like that. And here we go. Now we can see the evolution over time, as I look from left to right, of both the number of dollars per year we spend on fireworks and the number of hashtags. There's one more trick I want to show you as far as trend lines in Excel. If you're comparing two different trends on the same graph, sometimes it can help see a correlation if I click here, and then notice on the right it pulls up Format Data Series, and it says Series Options, Plot Series On, and it gives me a choice. Do I want to plot this blue series on the primary axis or the secondary axis? When I click secondary axis, now it will plot the blue series against these numbers on the right, and it's created another vertical axis for me, and I just have to make those numbers black as well, because I don't know why they start off gray. Another thing you might do is just boost the font size to like an 11, and that's going to make it easier for your audience to read as well. Okay, now that is a nice looking trend. And let's also go back and see what we were supposed to do. We were supposed to draw another scatter plot so I can view the correlation. And if I want to view the correlation between a predictor variable like dollars spent on fireworks and response variable like number of hashtags, I'm just going to select these two columns, and then I'm going to insert a scatter plot like this. And notice there's only 4 dots here, and each dot is representing a pair of dollars spent on fireworks along the horizontal axis, and then number of hashtags on the vertical axis. So this is a pretty decent looking scatter plot for this particular thing that we have going on. Okay, so if this were a perfect linear positive correlation, we would see all 4 of these dots in a row pointing up, and if it were perfect linear negative, you'd see all 4 dots in a row pointing down. In this case, it doesn't seem to me like there's a very strong correlation, but I don't just have to guess about it and tell you how I feel, because we can actually calculate the linear correlation coefficient for this data. And so the first thing I'm going to do is find the sample mean and sample standard deviation of both of these variables. And then what I'm going to do is sort of create the same table again, but here in this table, I'm just going to put the z-scores in this table instead of the actual values. So let me show you how that works. Sample mean in Excel, the easiest way to do it is just to average those 4 numbers. So I type in equals average and then put that range in parentheses. If you wanted to, just to see how it's calculated, this is equals, open parentheses. My numerator is going to be just the sum of these 4 numbers, and then I'll divide by the number of measurements here, which is 4. And that's another way to take the sample mean of each variable. And then the sample standard deviation in Excel, I type in equals stdev.s. Don't use the .p version. We only want the .s for sample standard deviation. I select that range, and that tells me the sample standard deviation. Again, another way to do this in Excel, because you know, if you want to see how it's done, this is the same thing as square root, open parentheses, what's underneath the square root for standard deviation, right? It's actually quite a bit. We have to take a numerator where we're adding up all of the deviations squared, so a measurement minus the mean, square that, plus the next measurement minus the mean, square that, plus the next measurement minus the mean, square that, plus finally the last measurement minus the mean, square that, and that's my numerator, so I close parentheses, divide by my denominator, and my denominator is n minus 1, so that'd be 4 minus 1. I'm going to put parentheses around 4 minus 1, otherwise it's not going to calculate right. And I put another closed parentheses to close up the square root function in Excel, and that would be the sample standard deviation. Now notice I did my 2 variables separately. I did not combine the data. That would really, mess things up if I had combined the data. And just to prove to you that, this works either way I do it, let's punch in the standard deviation sample for Excel and just do that data, and boom. The same thing as if I calculated it out all by hand. And then if I move this over and calculate all this stuff by hand, it should be 25.8. Yeah, so again, the by hand calculation and the sample standard deviation function in Excel both do the same thing, and so you might as well just use the Excel shortcut so you don't have to do everything by hand. Got to make sure you're referencing the right ranges though. There we go. Perfect, and here we go. Now that I have my sample mean and sample standard deviation, let's calculate z-scores. And every measurement has a z-score. And if you forgot what I mean by z-score, please go and watch the video on section 3.4 where I discuss z-scores, and remind yourself of z-scores because that's an important concept here in this class. For z-scores, I'm going to type in equals, open parentheses, the measurement minus the mean, close parentheses, divided by the sample standard deviation. So the z-score is the number of standard deviations a particular measurement is away from the mean. And so hopefully you can see that happening in that formula. Now I want that mean to stay in place whenever I drag this formula down in Excel, so I'm going to use a $8 to lock row 8. And then I'm also going to use $9 for the same reason. I want to lock in place the row 9 cell reference. And now I have a table with z-scores for all 8 of my measurements. Okay, I've got the z-scores. Now, what I want to do is find the product of these z-scores. Because let me go back to my PowerPoint, because I think we could all use a reminder about what we're doing here. I know it's been a long video, a lot of content here in Chapter 4. Doing my best to keep it brief, but let's rewind the slideshow back to where we were talking about how we're going to calculate the linear correlation coefficient. And how we're going to calculate it is this formula on slide number 12. We're taking the sum of all of the products of the z-scores for each of my experimental units. By the way, here in this data set, an experimental unit would be one particular year. So like 2010 is an experimental unit, 2011 is an experimental unit, 2012 is an experimental unit, 2013 is an experimental unit, and that means I have 4 experimental units. So I'm going to take a sum with 4 terms, where each term is a product of the z-scores, and then I'll divide by 4 minus 1, so I divide by 3. So the product of the z-scores, I'll do that times that, boom, and I take the product for all 4 years, and I have to take the sum of this, and so I'll type in equals SUM for sum, and select those 4 z-score products. So we've got the sum of the product of the z-scores, and now to finally calculate R, which is my linear correlation coefficient, I'm going to calculate this by taking the sum of the product of the z-scores and then dividing by n minus 1, or 4 minus 1, since my sample size was 4. So my linear correlation coefficient here is 0.29. Let's compare that to the critical value for this linear correlation coefficient for R when n is equal to 4. So now I have a sample size of 4. What's my critical value for R? I still have this table out. So n is 4. My critical value is 0.95 according to my table. So that should be 0.95. And we say, well, my linear correlation coefficient is less than 0.95, but it's still greater than negative 0.95. And so this means that there is not enough evidence to say there's a correlation. We say there's not enough evidence given by these 4 years to say that there's a correlation. And I think you can agree that these don't look particularly convincing. Before this little example is over, let me show you a few more things. There's a shortcut on Excel to calculating the linear correlation coefficient. You just type in R, and then you type in equals. Well, so the R is, by the way, the R is unnecessary. I'm just labeling stuff as I go. So what really matters is I select an empty cell, and I type in equals CORREL, open parentheses, where it says array 1, I want to select my my predictor variable, and then I'm going to type in comma, and then I'm going to select all of the data from my response variable. Close parentheses, hit enter, and boom. That value from the shortcut method has the same value I got by calculating the whole thing by hand. So it's a good way to check yourself and make sure you did the calculation correctly. Finally, before I move on, one last thing I'm going to do. Back to this scatter plot, where remember my horizontal axis represents values of my predictor and my vertical axis represents values of my response. Click anywhere on one of these blue dots that represents an experimental unit, and then go up to this green plus sign where it says chart elements. Click, and then there's a open square box that says trend line, so check that box that says trend line. Go over here to this arrow to the right, go down to more options. On the right hand menu over here, it opens up more options. What I need you to do next is click on this 3 little bars that say trend line options. At the very bottom, it says display equation on chart. Click that, and we have the formula for that little dotted line. And at the same time, if we go back to the trend line options, it also says display R squared value on the chart. And so I want you to know where that is. Of course, we haven't talked about this in this lesson, but we will in the next video talk about these things, and I want you to know where to find them on Excel, so it never hurts to see things twice or 3 times or 4 times, right? I'm trying to help you retain the important memories here. So we're done with that example, as far as I know. Let me find where we left off in our slides. Here is another example of linear correlation that I found. And this is a correlation that I found last semester whenever I was teaching statistics. I collected a bunch of data about the attendance of my students and their scores on a particular midterm test. I think in the left column, this is the number of days they attended from the first day of the semester up to the first midterm exam. And these are the scores from the first midterm exam. And, well, I think there were 10 total class days before the exam. And so the most a student could attend was 10 days. And what I wanted to do is see, is there a correlation between this data? Because I would think that the students who are attending class more often are hearing what they need to hear in order to learn and be prepared for the exam. So I'm thinking that attendance should correlate with exam score, and let's see if it does. So performing the analysis, I first drew a scatter plot of this data to see if there was a correlation visually. I noticed there's something, my pet peeve that I forgot to do is the default charts in Excel come with gray font, and it's really important to me to turn that font into a black font color so it sticks out better and is more easily readable on a PowerPoint. So that's my bad. Oops. Example of what not to do. So there we go. There's my scatter plot. So on the horizontal axis, this is representing number of days a student attended class. And on the vertical axis, this is exam score. And what I'm going to do next is show you an optional step that you can choose to do, but you don't necessarily have to. This vertical line is going to be the mean days of class attended. And this horizontal green line represents the sample mean of the exam scores. It's the average exam score, right? And so I say this is an optional step, and you might choose to do this because it helps us visually recognize that there might be a linear correlation here. And the reason I say there might be a linear correlation is because there's more dots that happen in these quadrants, the upper right and upper left, sorry, and bottom left quadrants, than there are dots that appear in these quadrants. Since there's more dots in the blue quadrants than there are in the orange quadrants, that suggests a positive linear correlation, I should say, emphasis on the positive. If it were the other way around, and there were more dots in the upper left and bottom right quadrants, that would suggest a negative correlation, and if there were the same number of dots in all 4 quadrants, that would suggest no correlation. But anyways, that's just preliminary evidence. It's a little bit, it's not numerical, right? It's a little bit more how you feel about it, but it's becoming more numerical to say, yeah, these dots concentrated in the upper right and bottom left, they're sort of suggesting a positive linear association. And now that we've done that extra optional step, we calculate the correlation coefficient for this data. And so putting this in Excel with that cell formula I told you, CORREL, I calculated a linear correlation coefficient of 0.456. And so that's not a super strong correlation. It's a correlation, but it's not super strong. In fact, what we would want to know is what is the critical value. And for the critical value, I have to know how many measurements did I take. So let's count. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are 20 students in this class. So when I ask what is the critical value, I need to know that my sample size was 20. Let's go back to our table and whenever my sample size is 20, the critical value is 0.444. And so we say that yes, because my critical value is 0.444 and my correlation coefficient is greater than that, we say that yes, there is enough evidence to conclude that the data is correlated. So there was enough evidence here to conclude that attending math class really does correlate with higher exam scores. So we can conclude with a good degree of certainty. By the way, you don't need to know this. I probably should have just not included this. But we can conclude with a good degree of certainty that attendance and test scores are correlated. And just by the way, in case you were interested, I remember for the same class, we could conclude that homework completion and test scores were correlated, but it actually wasn't quite as correlated as attendance was. So it had a slightly lower R value, which at this point I don't remember because this was, 6 months ago. All right, so that's it for section 4.1. If you have any questions about these concepts, I really do like chapter 4, and I've used chapter 4 material quite a few times in my professional life as an engineer, so I'd be happy to answer questions about this, and I'll see you guys in the next video.